This problem and all other data structure problems can be found here at Sarai Studies. Link is in the description box below. Today we're going to talk about binary heap trees, which are different than binary search trees. Binary heap trees are a data structure that supports priority queues, like in an emergency room, who needs to be checked first, who needs to be checked last. And so a good data structure to support that system would be a binary heap tree. There are two different types of binary heap trees. One is where you see the big number at the top. That's called a max heap tree, or we can say that this is in max heap order. And then another one is when you see the smaller number at the top. That's called a min heap tree, or we say that it's in min heap order. And that makes sense, right? Big number, max, small number, min. What they really mean when they say max heap is that the parent is always bigger or equal to both of its children. So in this case, 16 is bigger than 14 and 10. And if you look over here, 14 is bigger than both of its children, 8 and 7. Over here, 10 is bigger than 9 and 3. Over here, 8 is bigger than 2 and 4. So we know that this is a max heap binary tree. In min heap, the parent is always smaller, right? So both of these are based on the parent, but what about the parent? Here, the parent needs to be bigger than both of its children or equal to. Here, the parent needs to be smaller or equal to both of its children. So in this case, the parent here is 2, it is smaller than 3 and smaller than 9. If you go here, the parent here is 3, it's smaller than both of its children. Here, the parent is 9, it's smaller than both 12 and 20. And then the equal part, here the parent is 7, it's definitely smaller than 11, but it's actually equal to 7. So that's fine. The parent can either be smaller or equal to both of its children. And so that's really the first thing that's unique about binary heap trees, and that's their property. The second point is that you need to use levels to see the order of the numbers. What do I mean by that? Just split your tree into rows or into levels. So in this case, this is row 1, row 2, row 3, row 4, and so on. Same thing over here, level 1, level 2, level 3, level 4, and so on. The way that we look at a tree is by level, by row, from left to right. And then when we run out of nodes, we just move on to the next row or next level. So in this case, this is the first node. We ran out of nodes, so we go on over here to the next row. 2, 3. So notice how I'm going from left to right numbering. Then I just keep numbering, but when I run out, I go to the next row or level 4, 5, 6, 7. And then I run out, I go to the next row, 8, 9. Another thing that you might notice is that we have repeating keys now. That's different from a binary search tree. We had unique keys. We never had repeating keys there. So repeating keys are okay. Another thing is that a binary heap tree, in order for it to be a binary heap tree, it has to be a complete binary tree. What do they mean by that? They just mean that every row, every level has to be complete as much as it can be. For example, this row is complete as much as it can be because above it we have one node, and that one node at most can have 2 children. So this row can only have 2 children. Here we have 2 children, but each node can also have 2 children. So the most that this row, that this level can have is 4 children. So these rows, these levels are complete. All rows and levels have to be complete except the last one. In this case, we see if we want to specify null links. So there's no nodes there. So we can just say null. This last row doesn't have to be complete. It doesn't have to be full. So that's a property of a binary heap tree. So in other words, we just can't have this be null, or this be null, or this be null. But these here at the bottom can be null. That's fine. So all rows, all levels have to be full except the last one. And to be specific on point number 1, big number on the top, that means max heap. The parent is bigger than both of its children or equal to, then it's a max heap. For a min heap, it's a small number at the top. And also parent is smaller or equal to both of its children. So here the parent is smaller, 2 is smaller than both of its children, 3 and 9. Here the parent is either smaller or equal to both of its children. So those are all different ways to identify the type of binary heap tree. And finally, one thing that you might not have noticed is that we always start at index 1, so we don't start at 0. So we can represent priority queues using binary heap trees, but we can also represent priority queues using arrays. And when you have an array, your indices will be at the top and your keys will be at the bottom, and you'll have 0, 1, 2, 3, but you'll just not have anything in 0. Like you can have 0 there, but you can't put anything under here. But then you can have maybe 16, 14, 10, and so on, but nothing can be under the 0 index. There cannot be anything in here.